Welcome to Study Loop.
Okay, let's begin solving the problem 48. So it said this, if we have one loudspeaker and it's running towards the wall here with a velocity 80 meters per second, and by the meantime it makes the voice, and the frequency of the voice is 960 hertz. And at this temperature in the air, the normal speed of the voice is 344 meters per second. And on the wall, there are two holes there. There's a hole one, there's a hole two, and the distance between the two holes, we call A here. And you are supposed to standing at some position here. And this line, which is parallel to the wall, you moved up and down and found two special places. At those two places, the voice cancels, which means you hear nothing there. And you find that the angular position of those two special points equals plus 11.4 degree or minus 11.4 degree. So our question is, what will be the width between the hole 1 and the hole 2 here? We call that A here. And the question 2 is, if the velocity of the speaker equals 0, what will be the new theta, which means at those angular position, the new angular position, you hear nothing, or say the sound just canceled with each other. So to solve this problem, first of all, we need to basically introduce the Doppler effect and calculate the effective wavelength of the speed. So what will be the effective lambda here? If we have a source which didn't move, it will be simply the velocity divided by the frequency. It equals this. For us, it equals 344 divided by 960. We make sure all the units is in the international system, and it roughly equals to 0.3 7, oh not 7, 0.358 meters. But here we notice that we have a voice source is traveling, and the velocity of the source equals 80 meters per second. So here we have new wavelength. We call that lambda prime. It will equals lambda minus the velocity of the source towards the audience, or say maybe you are standing on the ground, divided by the by its original frequency. So it equals 0.275 meters. So we see that this is called a Doppler effect. It dramatically changes the wavelength of the voice from the speaker. So we will just use this lambda prime to calculate the first case, which is we have the theta equals 11.4 degree. So then we go back to use the equation of the interference. So I printed here the sine theta actually equals plus minus wavelength lambda over divided by A here. So here because we consider the Doppler effect, so lambda should be lambda prime here. And A is just the width of those two holes. And because you are standing far away, so we can use the small angle approximation, which say the sine theta is approximately equals the angle theta here. And angle theta is just 11.4 degrees. So we can write it down here. 11.4 degree equals, also plus minus here, equals plus minus wavelength, effective wavelength lambda prime divided by A here. So it equals plus minus point, how much? 0.275 divided by A here. And for convenient, or say for the calculation, we should convert the units of the angle from degree to the radians. So 11.4 degree equals pi times 11.4 degrees divided by 180. Here we have a dimensionless number here. So, and it equal, and we plug it in here. And it will be equals lambda prime divided by A here. So this will be the equation we want to solve. And we already learned that the lambda prime equals 0.275. So after the calculation, we get that our A equals 1.3814 meters. So this is question A's answer here. So okay, so suppose the loudspeaker just stop, but still keep making the voice toward the walls, and you are still standing on the same position, on the same line here, and you checked the new angular position here, and maybe at two different places, maybe here and here. You find that okay, I hear no voice, and the voice just cancel each other. So what will be the new theta here, which I will call the theta prime. So we still plug in the same equation here. So what we'll have that the new theta prime equals lambda divided by A here, and lambda will be just our original lambda here, which is 0.358 meters, and A, we already get A here, is 1.3814 meters, and we want maybe for a better comparison with the theta, we want to convert the unit from the radians to degrees. So it equals 358 divided by 3814 times 180 divided by pi here. And let's quickly calculate that. It's 0.358 times 108 divided by pi divided by 1.3814. So will be that. Okay, so it equals 14. 8.486 in degrees. Okay, finally it equals 14.844848. I'm sorry, it equals to the 14.8486 in degrees. Okay, so that's all for this problem. Thank you.